you're as bad as me.
Just take it on the phone.
How superior. Right, somebody with a pen, please. Oh, here's one.
There, Rob.
Twist it.
Wow.
Up in the team.
Oh,
Up in the
twist
team.
it.
Team player.
It's an intelligence test, I can see. Right. Tall equals, we'll leave out C. Sigma and sigma dash is sigma minus U. Right, thank you.
You're welcome.
Right, now we're talking soil mechanics now, not rock mechanics. I've already given you the bottom equation, the effective stress equation. The other, well, there's more than just two, I know, but another very important equation in soil mechanics is the one above. Tau is sigma tan phi. If it's clay, of course, it's got cohesion as well, but we're on sand, so I've left out the cohesion. So tau is sigma tan phi, that's the shear strength equation, and sigma dash is sigma minus U is the effective stress equation. Now what I want you to say, and these three who are talking all the time might be able to help, since they want to talk all the time. We were walking along the beach there, and constantly our heels and feet were sinking into the sand, and it was quite hard to walk. It's with damp, it's not dry sand, it is damp sand, but we were nevertheless sinking in. I'm sure you all noticed that. We've now come onto this bit of sand, quite close to the sea, and it's much firmer. But as you know, as we demonstrated earlier, if you go right down to the sea, you start to sink into the sand again. And as I'm sure you realise, if it's really dry, it just turns into a very soft material which you sink into again. What's going on?
I don't know.
Well, that's honest, I suppose. Doesn't show a lot of initiative, but it's honest. Well, we pointed out when this morning we were actually sinking into the sand when the water was right by our feet. I showed you this equation, and we said it's because the pore water pressure was rising because we were right by the sea. Now, as you come away from the sea, the water table drops, the pore water pressure drops, and the effective stress goes up. That's fair enough as a general statement. But why is it that as you go further again, even though the ground is damp, it's not that it's dried out. Oh, you're not talking again. If you can't contribute, keep quiet. I'm having to shout to be heard because I haven't got the megaphone. Now, as you go closer to the cliff there, we were sinking into the beach, as we were that end. Why? When it's damp and the water has by now withdrawn. So it's not that the pore water pressure is high, and yet it's firmer here than it is nearer to the cliff. Why do you think that is?
I don't know.
I'm not really expecting you to know, but I would quite like it if somebody made a few hazardous guesses, but you're not going to. Well, oh, sorry?
The sand's full of water, so the twist is...
Be quiet.
It is to do with water, you're right there. Well, really what it is that as the sea is going off down into, what's the word? The tide is dropping.
Subsides.
Yes, thank you. As the tide is dropping or subsiding, then the water in the beach also subsides with it. It follows it down to the sea. Now, when you're right close to the sea, then the beach is fully saturated and we were sinking into it. As you come away, the water level has dropped. But it doesn't only drop as it's dropping, you actually get, due to the physical movement of the water away to the beach, you actually get a suction pressure developed. So in effect, you not only does the pore pressure drop, it becomes negative for a while. And that means that this bit of the beach, which is far enough away, the water is draining away here beneath us quite quickly, is actually at its strongest because there's actually a negative pore pressure. And if you have a minus minus, that becomes a plus. And so the effective stress goes up because this becomes negative. So you've got minus U there, and minus minus is a plus, and so sigma actually increases. And then as it dries out, the negative pressure drops, because you can only have negative pore water pressure where you've got sufficient water in the voids. And with sand, because it's so porous, the water rapidly drains away and the negative pressure rapidly drops. And so as you go further from the beach, the negative pressure drops, and so the effective stress drops again, because the negative pressure is gone. Now this is rather subtle, but that is the case. Whereas with clay, you see, that's why clay has cohesion. You're all familiar with the idea of cohesion in clay. It's there because of suction pressure. But because clay minerals are tiny, tiny things, as I keep telling you, the suction pressure is much higher. But in sand, because they're so coarse, it has very low suction pressure, and it only lasts for a short time while the sand is damp but not dried out, but just a bit, well, like where we are now. As soon as it dries out a bit, it loses it. So we're on the bit that's got negative pore water pressure here as the water's draining to the sea. And then as the sea goes out, this will get softer and softer where we're standing now. And the bit that is quite hard will be behind us, near the sea. It happens all the time. Then when the sea comes in, it all reverses again. So this happens every day, twice a day on the beach. But it has, the principle is exactly the same inland as well. Only, of course, there you haven't got the sea coming in and going all the time, so it's not quite so obvious. But it's all to do with that equation there, sigma dash. But the reason I put this one is that the shear strength depends on sigma. And so as this sigma dash, if that drops, so does the shear strength. If that goes up, so does the shear strength. So that's why this equation and that one are both absolutely vital to soil mechanics. This is about the effective stress, and that is about the shear strength. But the one depends on the other. And when you good, here comes the megaphone. Great. I've been the speaker. Yeah, well, where is it? We're doing some basic soil mechanics, which they're loving.
I missed it all, have I?
Yeah,
We'll have to go back through it again, sorry.
I can send you my recording if you want.
No?
If you could,
Come on, have a twist, where are you going?
well, I want you to do under the
Where you going?
Could you grab the sheet? Absolutely vital.
Come on, let's get close together.
Hey, this is nice.
Hey, where you going?
Lovely.
Where you
Well, that's
going?
why I was hoping you'd help, because I can't do it myself.
I think we're getting too close
bugger.
together.
Could you hold it? Right, I'll help.
You hold that side. Get hold together.
It's like watching Titanic.
Oh, you want me to go under?
Under!
Oh, hey.
There, lovely. Okay, that was nice. Oh, I've lost the end. I'll have to take that. That's my glasses. If you could look after those as well.
Yeah?
Oh, my hand!
Oh, got it.
It's got wrapped up, that's why. It's all
God's
wrapped
fault,
round
that
the
is.
thing.
God wrapped it up before we went in.
Yes, there we are.
That's better.
Thank you.
Been good, Gareth.
Yeah, I think we get in there.
Yeah. Plug yourself in. Oh, it's good.
Right.
Testing, Gareth.
Testing. Is it working?
Reloading, Gareth. It is working. Try now.
Hello, hello.
Hello.
Hello?
Hello.
1, 2. Ah, that's better. Right. I rather lost the thread of what I was talking about.
It's underneath as well.
Yeah, I got it now, I think. Oh no, I haven't. Okay. Yes, well now I've got, I can speak more. Oh yes, thank you. I'll just repeat this bit about the equations. So, shear strength, which is what we rely on for bearing capacity and all the rest of it, is that equation there, and clearly sigma is part of the equation, and as sigma goes up, that gets better, and as it goes down, the strength drops off. So bear that in mind. Now then, what I was about to say related to this is when you put in soil anchors or rock anchors, what you are doing is increasing sigma. Because you drill a hole, you drop in a steel bar and you cement it in. And then you tighten it up. That's why on these rock anchors, you've seen lots of them now, they have a cap on top. And under the cap is a big nut. And you screw it up. And so you increase the tension in the bar, which is increasing the strength. Because I ought to do a little sketch of this. If I can find something without anything on it. There we are. A pen again, please. Thank you. Here is your Now then, what you're doing with a tie bar, whether it's in rock or soil, there is, I'm assuming rock in this case, there is the rock face, down there, the cliff face if you like. You drill a hole, you push your steel bar in, and then you cement it in. And then once the cement's gone off, or you can use glue, they sometimes use epoxy resin, but Portland cement is just as good. You cement it in one way or another, you give it time to go off obviously, and then this is a big nut at the end, and with a giant spanner you tighten the nut until you put enough tension to suit yourself. Now the point is, you take the bar beyond the failure plane. Now I haven't mentioned that before, I've kind of assumed it was obvious, but I suddenly thought it probably isn't that obvious. You take the tension bar beyond the plane that is failing. And that you'll have observed by mapping it. But mapping the area, and you work out where the failure plane is. And then you drill it, and you take it beyond, and then you see when you tighten it up, what you're doing is increasing the normal stress across the failure plane. And that increasing sigma, in other words. That's what the normal stress is sigma. And that increases the shear strength. I'll write it under here. Tau is sigma tan phi, or phi. Okay, tau is sigma tan phi. Tau is the shear strength. Sigma is the normal stress, which we've just been talking about.